Hi everyone, my name is Soyeon Kim and I'm active as Debite on GitHub. I'm a university student and an aspiring data engineer who loves exploring the depths of distributed systems. I've been contributing to Apache SeaTunnel project for the past several months. Today I'd like to share stories from my contribution journey, what I worked on, how I found the problems, and what I learned along the way. Let's get started. Part 1 is IMAP external storage compaction. Let me start with how I actually discovered this issue, because I think the process of finding it is just as interesting as the fix itself. I was reading designing data-intensive applications, specifically the chapters on storage engine internals, write-ahead logs, access tables, and LSM trees. One concept that really stuck with me was LSM tree compaction. The idea that you can write fast by appending everything and then periodically merge and compact those files to reclaim space and eliminate stale entries, I found that elegant. And then I had a thought, SeaTunnel uses WAL for state persistence. I wonder if it implements something similar. So instead of just reading about it in a book, I decided to go directly into the SeaTunnel source code and trace how the actual persistence layer works. I found a class called WAL Reader, which, just like in the book, reads back the write-ahead log and reconstructs state. So I followed the code further. I looked at IMAP's file storage, Cloud Writer, HDFS Writer, all the classes responsible for actually writing state to external storage. And that's when I noticed something. Every write call just appends new data. There is no cleanup, no compaction, no merging of all the files. The files just keep growing forever. And at that point it clicked. I just read about this exact pattern in DDIA. Append only write, unbounded growth, solved by compaction. The book describes it as a known, well-understood problem. And SeaTunnel's external storage has exactly this problem right now. The most frequently updated IMAP, engine running job metrics, gets written on every metrics tick for every running job. In a long-running production cluster, that file would grow indefinitely with no way to reclaim that space. So I filed an issue number 10329, and I proposed implementing a compaction feature based on exactly the LSM tree compaction model I had just studied. I think this experience really showed me the value of reading deeply. The book gave me the vocabulary and the mental model. The source code gave me the real-world context. And the combination of the two is what made it possible to spot a gap that others might have just accepted as how it works. The core idea was simple. Introduce a compaction mechanism that periodically merges all the fragmented, append-only written files into a single consolidated file, removing stale and duplicate entries in the process. I proposed two things in the issue. 1. Automatic compaction, triggered by configuration. For example, a size threshold. 2. Manual compaction, triggered by REST API or CLI, as a future enhancement. After that discussion, I got to work on the actual implementation. I submitted PR number 10399 a few weeks later. Let me walk you through the key design decisions. I chose a file size threshold as the default trigger. Conceptually, IMAP file storage has two kinds of files. One, mutable files, currently being written to. Two, immutable files, sealed, no longer accepting writes. Compaction is triggered when the total accumulated size of immutable files exceeds a configurable threshold, compaction threshold. Once that threshold is crossed, compaction starts automatically in the background. Why size-based rather than time-based or file count-based? Because size is the most direct indicator of the actual storage problem. You care about how much space is being wasted, not how many files exist or how much time has passed. When compaction runs, it reads the immutable files, deduplicates entries, keeping only the latest value for each key, writes the merged result to a new single file, automatically replaces the old immutable files with the compacted file. This is similar in spirit to how LSM tree compaction works in databases like RocksDB, if you're familiar with that concept. So that's the IMAP compaction story, a problem I discovered while reading source code. An implementation that taught me a lot about storage internals and performance trade-offs. While implementing compaction, I also spent some time thinking about different design approaches. At first, I was inspired by the concept of SS tables, where data is always kept in a sorted structure. But I also wondered, since the main problem in SeaTunnel is that external storage keeps growing indefinitely, do we really need to maintain a fully sorted structure? So I tried implementing compaction without using an SS table-like approach. However, this led to two problems. First, the compaction process became significantly less efficient as data grew. And second, it required to load a large amount of data into memory, which I found particularly concerning. Out of these two, the memory issue was the most critical. So I decided that maintaining sorted files was necessary, even if it adds some complexity to the write process. Another question I had was, do we really need compaction for every IMAP? Since compaction itself requires additional resources, including background threads, I felt we should be more careful about where we enable it. So I came up with the idea of making compaction configurable per IMAP. This allows users to enable or disable compaction depending on their use case. It might seem like a smart design decision, but I remember feeling really excited when I came up with it, because it felt like a practical solution to a real trade-off. Part 2 is implementing force stop for jobs. In a distributed engine like SeaTunnel Zeta, we expect jobs to finish or cancel gracefully, but sometimes they get stuck in a limbo state. I decided to tackle this by implementing a force stop functionality. The most challenging part of this task was the lack of debugging information. I received only a few lines of logs from a user issue, but it contained a crucial hint. If you look at the red box in this picture, you will notice something strange. One task is in the cancelled state, but another task is still stuck in cancelling. Why would the states be inconsistent? My hypothesis was the status report from the worker to the master was lost or dropped. When the master doesn't receive a final confirmation from the worker, it keeps the job in canceling forever. The job becomes a zombie, hogging cluster resources. To solve this, I designed the force stop mechanism in PR number 10075 with the bypass strategy. There are 2 points. First, master-centric authority. Instead of waiting for the worker's report, the master notice given the authority to independently declare a job as terminated. Second, aggressive resource reclamation. The master directly commands the resource manager to release loads. We don't care if the work is hung. We reclaim the resource first to keep the cluster healthy. Implementing this feature was deeply satisfying because it wasn't about having a mountain of data. It was about making a high-impact decision based on a single, critical observation. It taught me that in distributed systems, you have to design for the missing signals, not just the successful ones. Part 3 is a race condition bug fix. This story starts with another feature I was building, PR number 10133, report non-terminal job state. The original behavior was SeaTunnel only reported terminal job state, finished, failed, cancelled. Intermediate states like pending, scheduled, running were not being reported to the user in real time. I was implementing a fix so that all state transitions get reported immediately, giving users full visibility into a job's life cycle from the moment it's submitted. While testing these features, I noticed something odd. In about 50% of the time, jobs would show unexpected intermediate state transitions. It was intermittent. Sometimes it happened, sometimes it didn't. Classic sign of a race condition. The sequence I was seeing was lovely, pending to running, then scheduled, and back to running. That middle scheduled shouldn't be there. Once the job reaches running, going back to scheduled makes no sense. I started tracing the state transition logic in physical plan class. First, update job state is called to set the job to pending. At the same time, start job runs and sets its running to true. This triggers state process inside the first call, which transitions the state to running prematurely. Then start job continues and sets the state back to scheduled, only to flip it back to running again. Start job was always setting the state to scheduled as part of its initialization logic, without checking whether the job had already progressed past that state. Because this involved multiple threads racing against each other, the timing had to be just right to trigger the issue, which is why it only happened about half the time. Once I understood the execution order, the fix was clear. Start job needed to be synchronized. Part 4 is Reflections on Open Source Contribution. Looking back, all my contributions started from one thing, the willingness to go deep. I didn't want to just use the tool, I wanted to understand how it works. Whether it was tracing iFileWriter to find the compaction issue or debugging a race condition, I realized that theory and code accelerate each other. The more you read, the more you see in the code. When I first started, my only goal was simply to get my code reviewed. I just wanted someone to look at my work and merge it. But as I contributed more, and especially as I started reviewing other people's PRs, my perspective completely changed. I realized that the code review is a heavy responsibility that requires immense time and focus. It's not just about finding bugs. It's about protecting the project's stability and thinking about long-term maintenance. Now I don't just see reviews as the step to merge my code. I see them as a careful process where we take shared responsibility for the system. What I love most about open source is the progression. I started with smaller issues, but as I moved on to more complex problems, like the Zeta engine's force stop or compaction logic, I found a unique kind of joy. The harder the problem, the greater the satisfaction when I solve it. And what makes it even better is collaboration. Honestly, I enjoy contributing to open source much more than working on solo projects. Building something alone can be lonely, but here I get to communicate with brilliant engineers, exchange ideas, and solve high-stakes problems together. That synergy is what keeps me motivated every day. Lastly, I learned that technical skill is only half the battle. Explaining a complex design, responding to feedback constructively, and knowing when to push back, these are vital engineering skills. In a global community like SeaTunnel, clear communication is just as important as clean code. Before I wrap up, I would like to share a few practical tips and some personal reflections from my contribution journey. If you are new to open source, I highly recommend starting small. Look for issues labeled Good First Issue or Help Wanted. These are usually designed to help new contributors get familiar with the codebase. Another tip is to check user-reported bug issues. Among them, issues with detailed descriptions are often easier to approach because they already contain valuable context and reproduction clues. One of the biggest challenges I faced was contributing to parts of the system I didn't fully understand. There were many moments where I felt unsure or overwhelmed. To overcome this, I consistently tried to understand the codebase step by step. I also used AI tools to help validate my understanding or guide me in the right direction. But more importantly, I made a promise to myself: if I take an issue, I will not give up on it. Even when it took time, I tried my best to see it through to the end. I actually started contributing to open source simply because I wanted to try it. I was browsing GitHub, looking for issues labeled Good First Issue. That's when I came across about SeaTunnel. And that's how my journey began. The reason I kept contributing is simple. I felt that there was so much to learn from this project, and the maintainers were incredibly kind and supportive. When I compare myself before and after contributing, it almost feels like I knew nothing before. Of course, I still have a lot to learn, but this journey has helped me grow more than I expected. Before I finish, I want to say a huge thank you to all maintainers and contributors who reviewed my peers. Your detailed feedback and time have been my greatest teachers. I'm still learning, and there are many more challenges in SeaTunnel I want to dig into. Thank you for listening.